So the problem here is pretty simple.
What is going on?
Okay, there's like you have to click on the right half of the screen.
Oh, right half of the screen.
Okay, yeah. So the problem is that FTC, there's a lot of points that are dependent on driving. Like even in games with the autonomous world record, most of the points is scored by drivers, and drivers are humans, which means they're imperfect. Time comes, they get a little bit nervous with pressure, and anything you can do to take workload off drivers is kind of golden. So yeah, when you make driving easier for the driver, it removes a lot of pressure from the driver. And this is pretty important because when you optimize driver controls and have a lot of automated features, you can maximize the potential of a robot. Because even though you've worked so hard to build a robot, it almost means nothing if your drivers mess up in the last minute. So essentially, what this means is that optimized driving can lead to more points, which roughly equates to more wins. And a good example of this ideology being used is Tesla, because Tesla, you have a lot of features, and especially with the automated driving. Yes, it's still in beta, but the whole vision with that is that it makes driving easier. And the easier driving becomes, the more safer it becomes in cars and for robotics, the more points you can even score. So the first problem that software can be used to combat is drivetrain weight balancing. So we have this robot here. Can anybody tell me what will happen if I just ask all four motors to go forward at full speed? Anybody? Yeah, it will slip. It wouldn't slip, but more in terms of what direction would it go? If I want all four motors to go forward, would the robot go perfectly straight? No, and why is that? It's not because of imperfections. Sorry about that technical. Which is
The weight's misdistributed.
yeah, but yeah, the weight's misdistributed. So our robot, this is just a bird's eye view of our old robot design. And if you see B right here, it's kind of hard to see, but that's the center of mass. It's just a rough estimate, it's not accurate. But basically, because of that, when you send all four motors straight, it's gonna curve a little bit. And this is not what you want, but unfortunately, most teams have it coded so that this is what forward is. So the easiest way to counteract this would be by having each motor work a different amount than in theory. So in theory, forward is all four motors full power. But in practice, maybe you don't want one motor to go as fast so that you can counteract it. So the way you implement this with software is you multiply the final velocity sent to each motor by a constant in between 0 and 1. And the reason you want to do this is you can't go beyond 1 for motors because that would create like the maximum range is between -1 and 1. So you, instead of making motors go faster, you would want to make the slower motors go slower. So if you do this, you essentially counteract the problem. And the simplest method to know how much to multiply each motor is trial and error. You can calculate it, but trial and error still remains the easiest way. And as you continue to add subsystems, modify things, this is going to change. So the more you update this, the better it's going to get. And obviously, because you're dealing with unexpected forces, and say you have a bump on the field, this is not going to lead to perfect results because you're not using any encoder. You're just taking a guess. But this will definitely improve things. And the model with human drivers is that improvement is always good. So this is one way you can use it. So the next thing, when you're a driver, is anybody here driving for an FTC team? So when you're a driver, do you look at the joysticks when you drive?
No.
You look at the robot, right? So the easiest way I tested this out is Sam, he's our driver. What I asked Sam to do is I basically gave him a blindfold and I asked him to move it forward, backwards, left, and right. And what happened was that he didn't move it exactly forward. And you can't expect a driver to move it exactly forward with a blindfold. But that's what you're doing. When you're looking at the robot, you're not looking at the joystick. So every driver has what's called an error margin. So when you figure out what this error margin is, this differs from drivers to driver. What you have to do is you have to nullify all those zones within the error margins, and that's what I call dead zones. So you have two options for dead zones. The first option is an angular dead zone, And the way you find this out is by using arctangent. And you basically look at a point and say if the arctangent is within certain degrees, then you say, I just want that to go forward. So anything in this triangle, that's the same as going straight forward, because that's what the driver intends to do. He's not intending it to move in a slight in this direction. He wants to go forward. So that's, and this is a more accurate method. And the reason I say more accurate is because humans error in percentile. Now there's a second option, and that's easier to implement, and that's just an absolute dead zone. So if the joystick is a radius, circle with radius 1, you can just say anything from negative 0.2 to 0.2, just nullify that. But that's technically not how humans error. And the reason why this is not as accurate, if you take this point right here, that point gets nullified when the driver might want to go slowly. So that kind of creates redundant dead zones. But either method works, and it just helps the driver. So mechanism automation. So the thing about automation is we're not saying make teleop autonomous. You don't want to make driver control completely autonomous, and there's a reason why teams don't do that. It's because humans are still better, but certain parts you can take away from human workload. So what we define automation is you have a multi-step process, which would have earlier required 2 buttons or 3 buttons to do. Instead, you execute that whole process at one click of the button. So for example, move an arm up for 5 seconds, then the claw up for 1 second. This is an example of an automation. And there are numerous ways to automate, but when it comes to driver control period, sleep is not one of them. Sleep is one of the ways you can ask the robot to wait. But the problem is, if you ask the robot to wait, then the rest of the functions will not work. It's just a sleep in the code. So there is a much better way you can do this without using sleep, because sleep disables other movements. So a good example is our hang mechanism, which is right here. There are 5 parts to make it go from retracted to all the way up. And earlier we had it so that the driver had to manually do this, but now we made it 1 button click, because again, that sets the driver's mind so that he can do other things. So the basic logic, can anybody tell me a generic way you can try to automate something like move an arm up for 5 seconds, then a claw for 1 second? Any ideas on how you could approach this? Yeah?
Set the keyline so when you press a button,
Exactly, that's the first step. That's precisely the first step. So driver control is running in a loop, and you want to find the exact frame of the loop where the button was just pressed, which means it wasn't pressed the previous frame, but it was pressed that frame. So that's the exact button. And on that frame, there is one thing in driver control period that's pretty useful, the elapsed time of the program. You want to get that elapsed time. And why I put a photo of a sand timer is that kind of what we're doing here. By getting the elapsed time, we're basically resetting a sand timer. And then you set up an if statement. You get the current elapsed time minus the timestamp you just got. And based on what that is, you set certain actions to run. So the way this would look like is, say when I press the B button, 33 seconds have gone by in the match. From 33 seconds to 36 seconds, I can move the arm up. So by setting a timestamp, I basically reset a sand timer, and I say during this time I can do this. Yeah. So the last, or not the last, but another key thing our team had issues with is linear side movement. So I kind of want to show this. Our robot is completely off, and I'm going to move our linear slides all the way up. What do you think will happen when I let go?
It will fall down.
It's gonna fall down.
Exactly, it's going to fall down. So when you have even when the robot's on and the motors are not powered, when you bring it up, even if the motors are not powered but it's still on, it's still going to sag down. And that's just because of gravity. So the easiest way to counteract this is you need a force that the motor has to push to counteract that. So that's the easiest way you can do this. But there comes a problem, because our team used to do this 1 year ago. Actually, we're a rookie team, but I was part of a middle school team and I had this going. But the problem is, if you constantly have a 0.1 force or a very small force, what's going to happen is you're going to overheat the motor. And one of our motors actually started smoking. So, yeah, and that's not, yeah, it's because you're sending unnecessary power. So what we recommend is to use encoders to find out the motor, when the slides are all the way down. When the slides are all the way down, there's no need to apply this force. It's almost redundant. So you can save it and use encoders instead of a simple if statement. Now the last thing, and this is the thing that helped us the most, our robot isn't on and we don't have a battery there yet, but we have a lot of ways to get what's called feedback. So when the driver is driving in FTC, what's the one single sense that they're using to get feedback? Yeah, it's just sight. And they're almost using sight from the robot's point of view. But the thing is, because there are mechanisms on all parts of the robot, if that mechanism is not facing the driver, they can't really see it. So in autonomous, a lot of teams will set up sensors so that the robot can know certain things without any human intervention. But they don't really use that in teleop. And instead what they use is gestures and saying to the coach, oh yeah, we have 1 pixel. But the problem is, again, the more you rely on humans, the more imperfect it is. And our observations are not always perfect and it takes time. So what we recommend is giving feedback to the drivers that's automatic. So automated feedback mechanisms are more accurate and they save a lot of time. And this is pretty key because when you have the sensors on the robot, right. So when you have the sensors on the robot, like current sensing, color sensing, we actually have 2 color sensors on our robot, and we use this a lot in autonomous. But the key in our color sensors is that they tell us how many pixels we have and what colors they are. And this is an important feedback mechanism. So we have LED lights, and that's one way our team gives feedback. But LED lights are not the only way. In a lot of newer controllers like Xbox and PlayStation, you can also have gamepad rumbles where it vibrates, and it's almost like a reassurance that when you pick up 2 pixels or you do anything, you get the feedback as touch or something else. And that's very important because the more feedback you have on how your robot is doing, the more you're not thinking about it. So our drivers, we're not even concerned whether we picked up 2, we just look at the lights. It's very simple. So the more you simplify tasks, the better your drivers are going to drive. So yeah. So that's our presentation. Do you have any questions?
Yeah, so if anybody in person has any questions, feel free to ask right now. I think since we're a little short on time, we'll just have Keshav join the Zoom meeting later to answer any online questions.
Any in-person questions? Yeah.
The driver's license for the animation.
Do the drivers like? Yeah, well, the drivers, it's all about practice. Like what? Even when you get into a car that you don't own, it feels slightly different. So when you change a feature, everything is reliant on the drivers. Like I had a feature that I really wanted to use, but the drivers didn't like it. So everything is basically dependent on the drivers. The driver should never say no to a feature before you let them try it. But after they try it, it's all on their preference. If they like it, you go on with it. So in our case, automation did not affect the drivers at all because he had to press 4 buttons in a different sequence, and instead of pressing 1 button, it just saved him a lot of time, and he didn't have to think much. So it's all about getting rid of that habit. So it does save time. Any other questions?
For the linear slide problem.
Yeah.
Have you tried using the zero power behavior function to make it
The
break instead of
break?
neutral?
Yeah,
Does that work or not?
It works a lot better, yeah, but it still sags because again, the more force you have, it's not like a car brake where it physically disconnects the powertrain. And unfortunately, even if you set the motor zero power behavior to brake, we did try that. It still sags down. You still have to apply a small force.
It helps, but not enough.
Yeah, it helps. It's not like a car brake where it completely boxes. So yeah.
I think we actually have time for one online question. We have a question saying, why wouldn't you just counter spring slides rather than constantly power them?
Yeah, you can always add a hardware thing. You can counter spring slides. That's completely correct. You can always add hardware things. But this presentation is more about like your robot is built. You're coming into competitions. The builders will like focus on what they have to do. But yeah, our robot doesn't have any counter springs. So that's why yeah. if your slides are color screened to hold the position, then it will work, but I'm just talking for the slides that aren't, and specifically what our team did.
Okay, so give another round of applause for